Okay, so Unit 4B solo quiz distributions. This is the one we took this week, either Monday or today. So men's shirt sizes are determined by their neck sizes. Suppose the men's neck sizes are normally distributed. Hey, there's a good phrase. We know we're working with a normal with a mean of 15.8 and a standard deviation of 0.85. A retailer sells men's shirts, small, medium, large, and extra large that are defined in the table below. All right, so we have mean of 15.8, a standard deviation of 0.85. Just noting that down. Because the retailer only stocks the sizes listed above, what proportion of customers will find that the retailer does not carry any shirts in their sizes? Show your work. Okay, well, what does this look like? First off, what sizes don't they carry? They don't carry less than 14 and they don't carry greater than 18, right? So let's draw a picture of this. Standard deviation is 15.8. And right here we have 18 to infinity. And right here, we have 14 to negative infinity. So there's a couple different ways you can go about this. All right, there's a couple different ways you can go about this. I'm probably going to go about it the more, I don't know if it's more complex, but it's probably a little bit more complex, but it's just the way I think about it. I really need to add this area right here to this area right here, because they're not getting a shirt if they have a neck size bigger than 18, and they're not getting a neck shirt if they have a neck size less than 14. So I'm going to add those two together, and that's going to tell me the probabilities of what I need. So the normal, so z equals x minus mu over sigma. So I'm going to, my way is I'm going to have to do this twice. So in this case, the probability that z is less than 14 minus 15.8 over 0.85. All right, so that's the lower side. Over here, I have the upper side, probability that z is greater than, and I know I'm shading up because I know I'm have an up arrow, but a greater than inequality because I shaded up. So the probability of 18 minus 15.8 over 0.85. And once again, there's another way to do this, and we'll talk about that in a moment. But right now, I want to work at it this way. So I'm going to do this side first. Oh, and notice they said what proportion. And since they said proportion, they're asking for it. They're asking for an app. So if you're asking for an app, you're looking at a norm CDF. So I'm looking for a norm CDF because they're asking for an area, proportion, probability, percent. They're asking for one of the apps. So I'm going to do norm CDF for both of these. And I can go second vars, norm CDF, lower bound, negative 99999, upper bound, 14, because that's my highest part of my shading, mean 15.8, standard deviation 0.85, and I end up getting 0.0171. So less than 2% have a neck size less than 14 inches in this demonstration. All right. So then over here, second vars, doing a norm CDF. Now, looking at my shading, my lower bound is 18, and my upper bound is infinity. My mean and standard deviation are still the same, and I got 0.0048. So I need to add these two values. and I get 0.0219. So what that's telling you is a little more than 2% of their customers are not going to be able to find a shirt at that store. A little more than 2%. Okay, letter B. What proportion of men wear a size medium shirt? First off, again, we have, and I want to, before I forget about this, we have a 15.8 average neck size and a standard deviation of 0.85. So we're looking for a size medium. Well, size medium means we're working with 15 to 16. They've already told us this is normal. So my mean is here at 15.8. So when I look at this, it's like, oh, 15, that's the lower part. 15 is below 15.8, and 16 is above that. Seem to remember that. In one of my very advanced math classes. So that's the area I'm looking for. And remember, it's always z equals x minus mu over sigma. And technically, it's the probability that 15 is less than x is less than 16, because that's size medium. Notice I have two numbers. If I'm bound by something other than the infinities, I'm going to have to do two z-scores. And we always should start with a larger value, which is 16 in this case. So the probability that z is less than 16 minus 15.8 over 0.85 minus the probability that z is less than 15 minus 15.8 over 0.85. Okay, so I've gotten this far. This is adequate work. They're going to be happy with me. And so I can do this fairly quickly in the calculator, kind of in one step. And by the way, once again, they asked for a proportion. So they asked for an app. If they ask for an app, it's norm CDF. I keep forgetting to stress that, but I know that's an issue for you guys. So norm CDF, second vars, norm CDF, my lower bound is 15, my upper bound is 16, my mean is 15.8, my standard deviation is 0.85. And I end up getting 0.4197. So I end up getting 0.4197. All right. I don't know why I'm saying all right. I need to pause this. All right, letter C. What is the likelihood that a random sample of 12 customers have an average neck size greater than 16 inches? All right, so first off, what's my picture? I'm going to get to my keyword in just a moment. Or keywords, because I got several of them here. And they want greater, so I'm shading up. I'm shading to positive infinity. Now they use the word likelihood. All right. That is a word for probability. All right. What's the probability? What's the probability? So that makes that a norm CDF. So what's the probability that makes this a norm CDF? All right, so this is going to be a norm CDF. And notice I have a sample and I have the word average. Average tells me this is a X bar. All right, so we want the probability that X bar is greater than 16, which in this case means I need this formula. Z equals X bar minus mu sigma divided by the square root of n. So I want the probability that Z, we shade it up, so that makes this a greater than inequality, 16 minus 15.8 over sigma was 0.85 divided by our sample size of 12. Now hold on, guys. We have to be careful. I can only use the normal distribution if my sample size is 30 or larger. It's not. Or the underlying is normal. The underlying is normal, so we're good to go. So we can use the normal probabilities. So at this point, we're going to go to a norm CDF, second vars, norm CDF, lower is 16, upper, we shaded to positive infinity. So that's a bunch of 9s. Punch those in until I get tired, which at my age is pretty soon. 15.8, standard deviation of 0.85. Oops. Divided by the square root of 12, or 12 raised to the half power. And we get 0.0275. So about almost 21% of the population have a neck size, or neck population of these customers have a neck size that are size 16 or larger, about 21%. 21%. 15.62% of the customers wear a size small. Given a random sample of 13 customers, what's the probability that 3 will need a size small shirt? We have 13, so we're going to check out, we have a sample of 13, and we need specifically 3, all right? Another way of maybe saying this, besides the fact that this is 13 trials and 3 successes, 13 trials, 3 successes, clearly a binomial, but these are discrete probabilities. It's not a greater than, and no decimal responses, but really we have 13 customers. What's the probability 3 will need a size small shirt? So 13 customers, that's the number of trials. I need to make my number line. So 0, 1, 2, 3, 4. I always go 1 below, 1 above, dot, 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 all the way to 13. That 3, that is not more than 3. That's not less than 3. That's not at least 3. That's a singular value. So this is a singular value, and we already discussed it as a binomial. This is going to be a binomial PDF. I'm creating new abbreviations tonight. That won't confuse anybody, will it? All right. So we have 13, choose 3, 0.1562 to the third power, 1 minus 0.1562. 13 minus 3 is 10. That was pretty good for work. Second vars, binomial PDF, because it's a singular value, we only circled one number. Trials is 13. Probability is 0.1562. Our X value is 3. So 0.1994. Okay. Kidding about that. Don't get me in trouble. 15.62% of the customers wear a size small shirt. In a group of 14 customers, so we have a specific number. So this right there tells me probably working with a binomial. What is the probability that at least 4 need a size small shirt? So I'm probably working with a binomial. Well, I am working with a binomial because I have a fixed number of trials and I have a fixed, I know what my number of successes are. All right. So in this case, it's a binomial. And we have 0, 1, 2, 3, 4, 5, dot, 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 all the way to 14. At least 4 means 4 or more. So I need 4 or more. So I need the probability that X is greater than or equal to 4. So essentially I have to do the PDF of 4 plus the PDF of 5 all the way to the PDF of 14. Please remember, a CDF is just a sum of all the individual PDFs. So we can do this as a binome CDF, but we need to first show our PDF work. So our PDF work is going to be 14, choose 4, 0.1562 to the 4th power, 1 minus 0.1562. 14 minus 4 is 10, plus dot, 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 plus. So that's my lowest value that I wanted. So I started with the lowest value I wanted all the way to the highest value, which is 14.1562 to the 14th. 1 minus 0.1562. 14 minus 14 is 0. So there's my work shown. So we look pretty good at that. Now, they gave us the phrase at least, and by now you should shudder and eyes flicker and go into a spasm when you see at least. But you know it's a 1 minus, and you know it's a 1 minus the binome CDF. Trials is 14, probability is 0.1562. Now we have to be really careful. We take away what we don't want, and we want 4, we want 5, we want all the way to 14. So we take away the highest thing we don't want, which is 3. All right? So 1 minus second vars, binomial, CDF, trials is 14, probability 0.1562, X value 3, 0.1634. So the probability that at least 4 customers out of 14 need a size small is 0.1634. That's at least 4 out of 14. Okay, 15.62% of the customers wear a size small shirt. What's the probability that the first, oh, I love that word. It tells me probably a geo needing a size small is the 7th customer. It's specifically the 7th customer. If I'm making a number line, 1, 2, 3, 4, 5, 6, 7. It's not among, it's not before or after. It's specifically this one. So this means this is a geo PDF. So 1, 2, 3, 4, 5, 6, 7. This is going to be my success, which is 0.1562. So success, fail, these are all fails. A fail is 1 minus 0.1562. And I keep writing that, and I'm going to get really tired really quickly. So how about this? 1 minus 0.1562 to the 6th power times 0.1562 to the 1st. 7 minus 1 is 6. So GeoPDF probability is 0.1562. My X value happens to be 7. And by the way, you can show your work like this, or you can fill in all the blanks. I start the blanks and then I go, oh, it's this. But you have to show your work. You can't just go to the calculator. I know you want to, but you can't do it. Geometric PDF, 0.1562, X is 7, and we get 0.0563. Okay? So that was that one. 7.42% of the customer wear a size large shirt. What's the probability in a group of 17 men, more than 4 need a size large shirt? Group of 17. So we have 17 that were 17 trials. So this makes this a binom. So we know we're working with some sort of binom. And we need to make my number line 0, 1, 2, 3, 4, 5, dot, 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 all the way to 17. More than 4. Well, that means I need 4 is not enough. I need the probability that X is greater than or equal to 5. All right. Well, notice I circled more than one value. So this means we're going to be working with a CDF. But to show our work, we have to remember that a CDF is a sum of all the PDFs. So I have to do the PDF of 5 plus the PDF of 6 all the way to the PDF of 17. So we always do the lowest one that I want. The lowest one I want is 5. So 17, choose 5. 0.0742 to the 5th power. 1 minus 0.0742. 17 minus 5 is 12. Plus dot, 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 plus 17, choose 17. 0.0742 to the 17th power times 1 minus 0.0742. 17 minus 17 is 0. So now we look really good for work shown. So we need to talk about what we're going to do. Well, notice 0 is not circled. Since 0 is not circled, I have to do a 1 minus. We already said that we circled more than one value, so it's a CDF. And I want 5, so I'm not going to take it away. I'm going to take the highest value I don't want, which is a 4. So I have 17 trials, 0.0742 probability, and then X value of 4. So on the calculator, 1 minus second vars, binomial CDF, trials is 17, P is 0.0742, X value is 4. So 0.0065. All right, so the question was, how do I distinguish between a binomial CDF and a distribution of means? Great question. Distribution of means is specifically talking about the average or the X bar or the means. Whereas a binomial CDF is talking about the number of successes. It just has more than, it may have more than one success. It will have likely to have more than one success. It could be 1 success, 2 success, 3 success, but it wasn't talking about the average number of successes. If it was the average number of successes, probably working with a distribution of means. But if you're talking about how many success, the number of successes, you're counting them 1, 2, 3, 4, 5. So you're consequently that makes it a binomial because it's a discrete. 7.42% of the customers wear an extra large shirt. What's the probability that the first customer to need an extra large is among the first 10? First customer. Yay, that tells me we're working with a geo. And we have 0, 1, excuse me, it's a geo, so it starts at 1, 1, 2, 3, dot, 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 all the way to 10. And it says among the first 10. That means it could be the first one, it could be the second one, it could be the third one, it could be all the way up to the 10th one. So I have multiple values, so this is going to be a geo CDF. Remember, a CDF is just a sum of the PDFs. All right, so the sum of the CDF, the PDF means I have to do the first one. The probability of the first one is just 0.0742. That's very simple. Plus dot, 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 plus. Now, I have to do the 10th one, which means I'm going to have 9 fails followed by 1 success. 9 fails followed by 1 success. So that's going to be 0.0742 to the first power. That's off the page. That's not working. I should skip that down. 0.0742. That's my first success. Plus plus. These are going to be my fails. This is going to be my success. So my first success, 0.0742. That's to the first power. This is going to be 1 minus 0.0742. And 10 minus 1 is 9 because I have to have 9 fails. All right. So we said it was a CDF. Our trials, our probability is 0.0742. Probability is 0.0742. And our X value in this case is 10. Second bars, geometric CDF, probability 0.0742, X value 10. And the likelihood or the probability that the first person who wears a size large shirt is among the first 10 customers is about 53%. All right? About 53%. There were 5,317 previously owned homes in a Western city in the year 2000. Distribution of sales prices of these homes was strongly right skewed, with a mean of 206,274 and a standard deviation of 37,881. If all possible simple random samples of size 100 are drawn from this population and the mean is computed for each of these samples, what is the standard deviation of the sale prices of the sample? Show your work. Ooh, this one, they really messed you up. Sale prices of the sample. That says sample. It does not say sample means or the sampling distribution of the X bars. It doesn't say sample means. It doesn't say sampling distribution of the X bars. It doesn't say the sampling distribution of the means. It doesn't say sampling distribution of the averages. So consequently, this follows the what is the standard deviation of the sale prices? The standard deviation of the sale prices of the sample will be the standard deviation of the population. So number 2 is essentially 37,881. So number 2 is just 37,881. We can't divide by the square root of n because it's not the sample means. It's not the sample means. It's just the distribution of the sample. I'm going to hold off questions until I do number 3 because I want to contrast this with number 3. All right, because I think that's going to be helpful. So number 3, let X be a random variable that has a skewed distribution with a mean of 10 and a standard deviation of 10. Based on the sample of size 400, the standard deviation of the sampling distribution of X bar, the sampling distribution of the means, the sampling distribution of the averages. Because we're dealing with the sampling distribution of the means, the sampling distribution of X bar, the sampling distribution of the averages, this is our formula. Sigma divided by the square root of n, which in this case would be 10 divided by the square root of 400, which is just 0.5. All right, so the difference between these two is the sample. The sample values, the sample scores, the sample numbers always follow the population. The population was skewed, so the sample is skewed. But this is the sampling distribution of X bar, and because our sample, well, in the sampling distribution of X bar, or the sampling distribution of the means or the averages will always have this for my standard deviation. And it will have that even if the sample size is 30 or larger. Even if the sample size is 30 or larger. Is this supposed to be a 400? Yes, it is. Yes, it is supposed to be 400. All right, I'm going to open up this question. Golf balls must meet a set of 5 standards in order to be used in professional tournaments. One of these standards is distance traveled. When a ball is hit by a mechanical device, iron barring with a 10-degree angle of launch, a backspin of 42 revolutions per second, and a ball velocity of 275 feet per second. They gave you a bunch of information to scare you. The distance the ball travels may not exceed 391.2 yards. That might be important. Manufacturers want to develop balls that will travel close to 391.2 without exceeding that distance. A particular manufacturer has determined the distance traveled for balls it produces are normally distributed with a standard deviation of 4.3 yards. This manufacturer has a new process that allows us to set the mean distance the ball will travel. If the manufacturer sets the mean distance traveled to be equal to 386, what is the probability that a ball that is randomly selected for testing does not travel too far? So we know that we are working with a normal distribution, and we know that the mean is 386. The standard deviation, they tell us, is 4.3. And we're not supposed to exceed 391.2. Now the question is this an X or an X bar? That a ball, that's a singular, so this is an X. So we want the probability that X is greater than 391.2. So Z equals X minus mu over sigma. Let's start plugging in to see what we have. Probability that Z is greater than 391. Oh, excuse me, does not travel too far. I shaded that the wrong direction. I'm sorry, I should have shaded it this way. Because we want not, does not travel. I should read more carefully. So that needs to change. And this needs to change. This needs to be less than. Sorry about that, guys. $391.2 minus 386 over the standard deviation is 4.3. And our sample is size 1, so we don't need to divide. Second bars, normal CDF. And I know it's normal because it says they're asking for the probability. If you ask for an app, it's a normal CDF. 391.2, mean of 386, standard deviation of 4.3. The probability does not travel too far is 0.8867. Probability does not travel too far is 0.8867. 4B, if the manufacturer tests 6 randomly selected balls, so now I'm sitting there going, okay, I got 6. Is this a binomial or is this going to be the normal? Let's see. What is the probability that the mean, oh, winner, we know that this is going to be a normal because the binomial doesn't talk about that. So if the manufacturer tests 6 randomly selected balls, what's the probability that the mean distance exceeds the maximum of 391.2? So they've set this thing at 386. We want to know 391.2. We have more than one, and they say mean, so we're working with an X bar. So we want the probability that X bar is greater than 391.2. What's the probability that x bar is greater than 391.2? So since it's x bar, it's z equals x bar minus mu sigma divided by the square root of n. So that's the probability that z is greater than 391.2 minus 386 over 4.3 divided by the square root of 6. Now, they are asked for the probability. So they asked for an app. If you ask for an app, it's a normal CDF. Second bars, normal CDF. Looking at my shading, my lower bound is 391.2. My upper bound is infinity. The mean is 386. My standard deviation is 4.3 divided by the square root of 6, and I always just raise it to the half power. That's the way I do it. You don't have to do it that way. And it's pretty small chance. It could happen, but it's pretty unlikely that an average of 6 balls would go farther than 391.2. Okay? So the question came up, how did I know to use the x bar equation? Well, first off, we're working with a normal curve because they tell us it's normal. And then it says a probability that the mean. Well, I have two basic choices. If I'm working with a normal, I have basically two choices. I have z equals x minus mu over sigma, and z equals x bar minus mean over sigma divided by the square root of n. And since the mean distance, they're asking for the average distance, they're asking for the average of the 6 balls, so they're asked, this right here maps to that, and that's how I knew to use that. Although having a sample size is a really good hint. If I have a sample size, it's probably this, but I need to look for the mean or average or x bar to indicate that, to formalize information.
No.
All right. If the manufacturer wants to be 97% certain that a randomly selected ball will not exceed the maximum distance of 391.2 yards, what's the largest mean that can be used in the manufacturing process? So, what do I know? I don't know this, because I got to figure that out. They're asking me for the mean. I don't know the mean. 391.2, and this area right here is 0.97. We know from up above in the equation that we're dealing with a normal. And guess what? They gave me the app. If they give you the app, you need to think inverse norm. All right? They give you the app, you need to think inverse norm. So z equals x minus mu over sigma. I need to plug in what I do know. What I know is I can't exceed that value. So that value is 391.2 minus a mean. I don't know what that is. I know my standard deviation is 4.3 because they told me that. Now, what I do know is because I have a 0.97, I can do an inverse norm. And like I told you all earlier this evening, if you do an inverse norm, you have to give the z-score. So I have to give the z-score, which in this case is 1.880. And then I'm going to solve by algebra. So times 4.3 minus 391.2 and I get a negative 383.1125, and people are freaking out, but it equals a negative mu. I make both of those positive, and so this becomes my answer. And that makes sense. I need a mean that is less than 391.2. If my mean's above it, that didn't work because I can't exceed that value. I have to be less than that. And that's what our drawing shows. Okay, that's a tough question.